This equation I'm going to put up now describes everything we know about the universe, except gravity. So everything from the way atomic nuclei work, the way that atoms and molecules stick together, the way that light interacts with atoms and molecules, the radioactive decay, the way stars shine. At a fundamental level, everything we know about the universe at the start of the 21st century is in this equation. But there is a problem with it. It's a prediction, lies in these last two lines. See, the first two lines contain symbols which represent all the particles here. So all those things are combined in these symbols, the forces of nature, electromagnetism, all those forces, the nuclear forces that stick the nucleus together, all described in the first two lines. The bottom two lines contain this symbol here, which is a Greek letter phi. And that represents a particle that is not here. It may not even exist, but it's predicted to exist. In the spirit of Richard Feynman, we have to go and look for it. And this is one of the key things the LHC does. So this thing is called the Higgs particle that you may have heard of. It's a particle that's predicted to exist in order for our theory to work. So it's really, you sit down, do maths, it doesn't work, you find a way of fixing up the maths so it describes the things you can see, and the only way, or the simplest way we found of doing that is by introducing this new thing. What does it do? Well, it gives mass to everything in the universe. So if you look at your hand, it's made of subatomic particles and they have mass, they have substance, obviously. What we found about 50 years ago now is if you just write in the masses, you say electrons got a mass. We weighed it back in 1897, actually. Let's just put it in our equations. Turns out that the whole thing failed. What was found by a scientist called Peter Higgs is that you can introduce mass in a very interesting way, a clever way, which makes those equations work. The universe, says Peter Higgs, is full of a field called a Higgs field. So you might imagine that this room is full of something called the Higgs field. Everything has to pass through it. If you think of a massless particle like light, so light's a stream of particles flying around the universe, they don't talk to the Higgs field. That means that they get no mass. They pass through the universe unimpeded. But the electrons and the quarks and everything that makes up your body, those things have to talk to the Higgs field. They interact with it. They get dragged back by it in some way. So they acquire mass. They can't pass through the universe at the speed of light. That mechanism, which is quite simple, is actually our best theory of how mass appears in the universe. If that's true, then we have to find these things, the Higgs particles at the Large Hadron Collider. If it's not true, then we know that we will see the origin, the process, I suppose, which causes mass to enter the universe. But I think the key thing to remember is that this is our theory of three of the four forces of nature. So everything that happens in the universe other than gravity at a fundamental level is represented by this theory.